Your AI app probably works fine right now because nobody is using it. Scaling AI systems sound easy. Just add more workers. Not really. Because the moment traffic increases, queues start to back up, workers get overloaded, database starts to slow down, retries multiply, and due to all of the above, the costs start to explode. And suddenly your fast AI apps becomes practically unusable. Most developers think that scaling is just make the model faster, and many do just that. And what do they see? That the change in request processing time, or you can say the change in request processing speed, is practically negligible. Initially it would have been taking 5 seconds, now it's taking 4.98 seconds. So that's the thing they see. Real bottlenecks are usually somewhere else. They are at queue, either at database, worker coordination, and the infrastructure costs are the real bottlenecks. Scaling is really about pressure management. Unless you are using truly slow model, like you are using such a model that it is truly very slow. Changing the model is going to change practically nothing for you. In theory, concurrency sounds amazing. More workers means more job processed at in parallel, and you will get higher throughput. But AI workloads are heavy. Each worker is going to consume memory, CPU, database connections, and model records. So increasing concurrency aggressively can actually reduce stability because many risks with parallel processing, like one job got processed by two or more workers, increase significant. Also, more parallelism is not free. You have to pay for it. But eventually, what happens is that one machine stops being enough. So now you have to add more workers. This is called horizontal scaling. Now jobs distribute among multiple instances, which is going to improve your throughput. But it creates new problems. Queue contention, duplicate processing, database pressure, retry amplification are some of those. Scaling creates complexity faster than people expect or people realize. There is also one more skill, which is called vertical scale. In this, what happens is that you upgrade the hardware on which the worker is running. Basically, you can say that, okay, worker initially had, let's just say, 32 GB of CPU. Now you have made it to 64 GB of CPU. That is called vertical scale. That is also a practical solution and it is used, but it also has its own limits because two machines of same caliber, like let's say two machines of 32 GB CPU and one machine of 64 GB CPU, they have a like very significant cost difference. So it generally happens that after a point, those two machines are cheaper than the big machine, or you can say the advanced machine. This is where systems silently fail. Jobs enter faster than workers can process them. Now, latency spikes, users have to wait longer, retries increase, queues grow infinitely. And the most dangerous part about this is that system is technically working. It is technically correct. It is just working way badly than anyone expected. This is a bottleneck which people underestimate. Workers finish AI process, then they have to wait for the database writes. Like worker is like, okay, I have processed everything. Now this is the output. Database take this output and write it. So what is happening here? Your expensive AI infrastructure is sitting idle while it is waiting for storage operation. Terrible economics. Because you want that your AI system or your AI infrastructure is not sitting idle. It is processing new requests, especially when storing embeddings, logs, chat history, analytics, and job states. Eventually, your database becomes slower than your model. This is where engineering becomes economics. See, you can keep scaling. There is no theoretical limit. Okay, then after this, you can't scale. You can have more GPUs, more workers, you can have more infrastructure, but eventually you have to ask it to yourself that what you are thinking, is it financially sustainable? Because at the end of the day, GPUs and infrastructure are real world architectures and real world resources, and you have to pay for it. Sometimes reducing concurrency improves efficiency, sometimes batching similar jobs is smarter. The fastest system is not always the best system, and the best system all is not always the fastest system. Let's just say users upload a resume into an AI analysis system. At small scale, one worker is handling the requests, queues stay healthy, and responses feel like they just arrived in an instant. Then traffic spikes. Now, 500 jobs enter the queue. Workers are saturated. Retries increase. Database CPU usage spike. And you have to add more workers then. So you added more workers. Now the queue improved, but the database latency became terrible. This is the real lesson here. Scaling never removes the bottlenecks, it moves them. And why did I say that database latency here becomes terrible? See, the more workers you have, the more database connections, or you can say the more open database connections you have. And the more open database connections you have, the more vulnerable your database becomes because this connection can be hacked. Also, on each connection, you have to make sure that each connection is not repeating the jobs. You have to manage the workers also. You have to manage concurrency and database also. So, this becomes a whole distributed system management thing. And if you read about the distributed database management, it will tell you that okay, there are many problems, like many underlying problems, and there are some real nightmares which, if you know anyone or you have talked to anyone who is working in data centers or we're dealing with real hardware, you will see them, they will tell you things which may sound exaggerated, but they are the truth. See, there is no perfect scaling setup. There is no hard and fast setup or hard and fast rule. Okay, that this is the rules. You scale according to them and you face no problem. See, higher concurrency is going to give you faster throughput, but it is going to lower the stability of system. More workers are going to give you lower latency, but your infrastructure costs will be higher. Aggressive scaling is going to give you better performance, but the coordination will become very hard. Eventually, every scaling problem becomes a resource allocation. Most AI systems don't fail because the model is bad. They fail because the infrastructure surrounding that particular model can't handle pressure. That's what real scaling is. Managing pressure across entire pipe. If you're building AI systems seriously, this is a layer that eventually becomes very important and it starts to matter the most.